Can you see my screen?
Yes, yes, Swati.
Okay. Welcome, everyone. Today is day three of our workshop, and our focus is quantum machine learning or QML. Over the last 2 days, we've built up all the pieces we need for this. On day one, we met with the basic building blocks of quantum information, starting with qubits, superposition, entanglement, quantum gates, etc. And on day two, we moved on into applications into security. We talked about quantum cryptography, and right at the end, we looked at anomaly detection, spotting unusual behavior such as fraud detections, network attacks, and sensor readings, strange sensor readings, and things like that. Today is where we pull all of that together. We are going to ask ourselves, how can we use a quantum computer as part of our machine learning system? Quantum machine learning is not about throwing away all of our existing machine learning tools. Instead, it's about extending them using quantum hardware as a kind of special purpose co-processor. Yeah. So, what exactly is quantum machine learning? At a high level, quantum machine learning is about using quantum computers inside machine learning workflows. It's not that the entire learning pipeline suddenly becomes quantum. Instead, we usually keep most of the pipeline classical and we insert quantum parts where they might provide extra power. For example, when you train a deep neural network on images or text, the CPU is in charge. It loads all the data, organizes mini batches, runs overall training loop, and all. The heavy numerical work, the huge things like matrix multiplications and all, is delegated to the GPU or a TPU. So we can imagine a similar story for quantum computers. The classical computer orchestrates the training process, while the quantum processor is called whenever we need to evaluate a particular quantum circuit. Most practical quantum machine learning algorithms, therefore, use a hybrid architecture, and that's what you will see on the slide. Uh, in the little diagram there, on the left, we have the classical optimizer, and on the right, we have quantum variational circuit. To explain this, imagine like a bank wants to detect fraudulent credit card transactions. Like each transaction has a features like transaction amount, country, time of the day, the merchant category, etc. The bank has historical data for each past transaction. They know whether it turned out to be normal or fraudulent. So, in a hybrid quantum machine learning setup, the loop might look something like this. The classical side is running, say, Python takes small batches of transactions and prepares them as inputs. Those inputs are encoded into quantum state and fed into quantum circuit on the quantum device. The quantum device runs the circuit, measures the qubits, and sends back classical numbers, for example, probabilities for the transaction is a fraud. And then the classical code compares those predictions with the true labels and computes a loss, how wrong we are, if it's a fraud or not. The classical optimizer then adjusts the parameters of the quantum circuit to reduce that loss. With these new parameters, the whole process repeats many times. So this back and forth flow of information is sometimes called a hybrid quantum classical loop. And it's at the heart of our modern quantum machine learning. Firstly, in the core concepts, we have variational quantum circuits or VQC. A VQC is a quantum circuit with tunable parameters, usually rotation angles or gates like RY, RZ, which are usually rotating on basis of y-axis, z-axis, and things like that. You can think of these parameters exactly like the weights in a neural network. During training, we keep changing those angles to make the model fit the data better. Uh, yeah. And secondly, we have quantum neural networks or QNN. A QNN is basically a VQC arranged in layers, similar to the layers of our neurons. Each layer might be a parameterized single qubit rotation, followed by entangling gates between the qubits. So a QNN behaves like a deep neural network, but the computation inside each layer is governed by quantum physics. And then we have hybrid models. In practice, almost everything we do today is quantum machine learning is a hybrid model. A quantum device is used for the parts where quantum physics may give an advantage, like processing high dimensional quantum states, and classical computer does the rest, such as data handling, loss calculations, optimizations, and things like that. Uh, yeah, yeah. Before a quantum circuit can learn anything, it needs to see the data. How do we encode this classical data into our quantum states? In classical machine learning, this step is almost trivial. Like you take a vector of numbers and then feed it to your network. In quantum machine learning, we need to turn that vector into a quantum state. This process is called encoding, or sometimes it's called feature mapping. Let's see, we've seen a little bit yesterday. So imagine we are in a building. We are building a simple model to predict whether a patient is at a high risk or a low risk for complications while you are monitoring them, like for the next 24 hours. So, what kind of features matter? Something like their temperature, their heart rate, oxygen saturations. These are the features that are important. So, how could we represent this information using qubits? First, we have different key concepts. So firstly, we'll go with amplitude encoding. In amplitude encoding, we pack all this data into amplitudes of the quantum state. A system of like n qubits has 2 power n complex amplitudes. So this can, in principle, store a lot of information very compactly. For example, with 3 qubits, we have 8 amplitudes. It's 2 power 3, 8 amplitudes. We could normalize 8 numbers and encode them as amplitudes of a single quantum state. In our medical setting example that we just took, those 8 numbers may be readings of 8 different sensors. The advantage of compactness is we can represent many numbers with relatively few qubits. The downside is that preparing such states can be complex and it's really costly on the real quantum hardware. And secondly, we have angle encoding. Here, each feature is encoded as a rotation angle of the gate on a qubit. For example, we might apply a rotation Ry of theta, where the theta will be proportional to patient's temperature after they observed the patient for a while. In our example, we could have 3 qubits, for example. The qubit one will be the encoding temperature of the patient, qubit two will do heart rate, and three will do oxygen saturations. We convert each of these measurements into an angle between 0 and, say, maybe pi. And then we rotate each qubit by that much amount. If it's very intuitive scheme, like larger feature value measures a larger rotation, stuff like that. And thirdly, we have basis encoding. Basis encoding is used for binary features. We simply just map 0 to 1 of the quantum state, like get 0, and 1 to get 1. And if we are doing like fraud detection, some features are basically binary. Like, is the transaction international? Yes or no. So, and then if is it an online purchase? Yes or no. So these binary can come under basis encoding. And for each of these, we use 1 qubit. And then we have feature maps. A feature map is not just a single rotation. It's a small circuit where job is to transform the input data into a possibly high dimensional quantum state, often using entanglement. The idea is very similar to kernel methods in classical machine learning. In kernel methods, we take data that might look inseparable in its original space and map it into a higher dimensional feature space where separation becomes easier. The feature space is a Hilbert space of the quantum system, which can be enormous. Here on the right, you can just see like a colorful cloud of classical data points. Imagine they're all patients or financial transactions. The feature map transforms them into points in a quantum or Hilbert space represented by that swirling structure on the right. Um, if we choose the feature map cleverly, data that was hard to separate classically may become easier to separate when represented as quantum states. In fact, the quantum kernel example we briefly saw on day two yesterday used the same idea. It used a specific feature map, the ZZ feature map in Qiskit, to embed classical data into quantum state and then computed inner products between those states as a kernel. Suppose we are building a spam detection filter for emails. For each email, we might have features like number of hyperlinks, whether it contains the word free or something like that, and then whether it was sent at midnight or at 5 a.m. or something like that. So if we see how we could encode this, the number of the links would be an as an angle or in one qubit. The presence of the absence or absence of the word free is a basis encoded qubit, one if present, zero otherwise. And the uh, sorry, and the nightmare feature as another basis encoding, like midnight transaction or not. Those qubits go through a feature map circuit that entangles them and creates a rich quantum representation of the whole email. That representation becomes like an input into our quantum model. Variational circuits and optimization. Now that we know how to encode the data into quantum states, we need a mechanism to actually learn from that data. The mechanism is the variational quantum circuit. Often we call it VQC in short. You can think of VQC as a quantum analog of a neural network. Firstly, parameterized gates. These are the quantum gates that depend on one or more continuous parameters, typically an angle. For example, a rotation around z-axis might be written as rz of theta 1, and around y-axis it could be ry of theta 2, as you can see on the right. The collection of all these theta values is our parameter vector, very similar to the weight vector of neural networks. During training, our goal is to find parameter values that make a circuit behave well on our particular task. In practical, when people say QNN, they almost always mean variational quantum circuit arranged in layers. It's very similar to what you can see in a classical neural network. In a classical neural network, we have layers of neurons with weights and biases. In QNN, we have layers of qubits with parameterized gates and entangling gates. The word variation circuit emphasizes the physics side, a circuit whose parameter we vary to minimize an energy or a loss. The word QNN emphasizes the machine learning side, where a network of the quantum gates that we train, just like a neural net. In other words, every QNN is a variational circuit, and most useful variational circuit can be viewed as QNNs. Then we have cost function. A cost function, sometimes called a loss, is a number that tells us how bad the model is currently doing. In a classical problem, the cost might be a fraction of misclassified examples or the cross entropy loss. In regression, it might be a mean squared error between predicted or true and true values. In quantum setting, what happens is we encode the input data into quantum state. We run the parameterized circuit. We measure one or more qubits to get probabilities or expectation values. We plug those numbers back into our classical formula to compute the loss. So the output of quantum circuit is always classical numbers. The cost function is also computed classically. And then we have classical optimizer. Once we have the cost, we need to decide how to update the parameter theta. For this, we use standard classical optimization algorithms like gradient descent, ADAM, optimizer, SPSA, and anything, but whichever you'd like to. The optimizer is entirely classical. It just uses information about the cost to propose new parameter values. If you want to take a real world analogy, think of tuning a audio equalizer in a music player. Each slider controls how much bass, mid values they have. You start with some default settings. You listen, decide the sound is too muddy, to you have to reduce the bass, or it is too high pitch, or something like that. And then over the iterations, you arrive to a setting that sounds good for you. It's something like that. So if you look at the diagram on your right, each horizontal line here is a qubit. Each box with the angle theta inside is a parameterized gate. The plus sign and the controlled connections represent entangling operations that led to different qubits and therefore different features interact. We can repeat these layers multiple times to build a deep variational circuit in, in the same way as a deep neural network. There are, of course, challenges here because real devices are noisy. In such cases, training becomes really difficult, and choosing the right depth and the structure is still more of an art than a science at that point. But despite these issues, VQC and QNN are like the workhorses of our quantum machine learning. Okay, coming to quantum classifiers and regression. The structure is very similar to what we've already seen, but now we explicitly separate it into like three different stages. Firstly, feature encoding. First, we take our input X. This could be a transaction or patient information or an email or a house if you're predicting its price or something like that. And we encode it into a quantum state using one of the methods from earlier, amplitude encoding, angle encoding. Oh, sorry. Was there a disturbance there? Sorry. Okay, where was I? Amplitude, we had amplitude encoding, angle encoding, or basis encoding in previous slides. And then uh, in the diagram on the right, oh, you can see the feature encoding blocks. And then after feature encoding, we have variational layers. Next, we pass this encoded state through one or more variational layers. These layers consist of parameterized gates and entangling gates. The blue blocks labeled R in this diagram on your right, the parameters of these layers are what we train. And then we have stage three where we do the measurement. We finally measure one or more of the qubits. The measurement outcomes or their probabilities are converted into predictions. If we want to take an example of spam detection, suppose for each email, we might extract a few features, like, for example, the fraction of words in all capital letters, the number of links, whether certain spammy phrases appear or not, or at what time of the day the email was sent. And here is like how a quantum classifier would work is if you go to the step one encoding, we map each of these features into qubits using angle or basis encoding. And for instance, the it contains the phrase free. Uh, it could be a basis feature like sorry, looks like someone's muted me. Don't do that, guys. Okay. Yeah. Yeah, we encode it into the email information. If we look into encoding, if it contains the word free, we can use a basis encoding where yes, it sounds like a spam email. And when you come to variational circuit or QNN, the encoded qubits go through several layers of parameterized and entangling gates. These layers allow the model to represent complex relationships. For example, the email is suspicious if it has many links and it is sent at like 3 a.m. in the morning, or there is everything used in all capital letters, or something like that. Measurement. We can measure this one particular qubit. We interpret the probability of getting outcome one as the probability that the email is a spam, or zero if it is not a spam. During training, we show the model many emails with known labels, spam or not spam. We compute a classification loss, such as cross entropy, and we update the parameters to minimize that loss. Uh, If we want to take a regression example, we can take one of how prediction of the housing prices, which is a classic machine learning example. Suppose we have the data about the houses, like how much is like a square meter area, and then its distance from the city center, average age of the building, or maybe the index representing local like school or amenities or close by, and their quality. For each house, we know the sale price, and we train the quantum machine learning model to predict that price. We can reuse almost the same structure, like we encode the features into qubits, apply variational layers for, like, we can take example QNN, and then we measure a qubit and take expectation value of some operator, usually like poly Z or something. The expectation value is a number between -1 and 1. We can linearly rescale it to match a realistic price range. The loss is now the mean squared error between predicted and actual prices. Over training, the parameters adapt so that the quantum circuit's outputs approximate the actual prices of the houses as closely possible as they can. By changing the encoding, the number of qubits, the circuit architecture, we can design new models for many types of data. Okay. So, yeah. Okay. Next, we have gradient-based training in hybrid systems. To train our quantum models effectively, we often want to use gradient-based optimizations, just like we do in classical deep learning. How do we compute gradients of a function that is defined by a quantum circuit? To answer that, in classical neural networks, we use backpropagation. We compute derivations layer by layer using a chain rule. Modern frameworks like PyTorch or TensorFlow do this automatically. In quantum circuits, we can't directly apply the same trick because the quantum state is not something we can freely copy or inspect it. We only get measurement statistics from running the circuit many times over and over. So looking at the formula on top of the slide on your right, here f of theta is a some expectation value that depends on the single parameter theta. For instance, the probability of getting 1 on a certain qubit after running the circuit. The parameter shift rule says to compute the derivative of f with respect to theta, run the same circuit twice, once with the parameter shifted up by pi by 2, and once with the parameter shifted down by pi by 2, and then subtract the results and divide by 2. We've now seen all the main ingredients of quantum machine learning: the hybrid quantum classical loops, data encoding, feature maps, variational circuits, QNN, gradient-based training, and all. So here, the obvious question is, where could quantum machine learning actually be better than classical machine learning? First, expressivity. The system of n qubit lives in a Hilbert space of dimension 2 power n.
अँ
That
अँ
means,
अँ 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 तँ चाहिँ नाटक गरेर यहाँ
excuse me,
पढेको जस्तो गरेर अर्काको चक्कर लाग्यो उफ्रेको हेर्दै बस्छ
sorry, sorry for that. Um, yeah, we have like n qubits in Hilbert space whose dimension will be 2 power n. And that means the number of possible quantum states grows exponentially with the number of qubits. Intuitively, this gives quantum circuits access to extremely rich function classes. The hope is that there are tasks where quantum models can represent patterns that classical models would need a very large amount of memory or computation to capture. Secondly, we have circuit depth. By stacking many layer of gates, much like stacking layer in deep neural network, quantum circuits can create very complicated, highly nonlinear transformation of input features. Depth gives them compositional power. Simple gates combine to create sophisticated operations. And then entanglement. Entanglement creates correlations between qubits that have no classical analog. In data science language, it's a very natural way of model strong non-classical dependencies between features. For example, in quantum chemistry, electrons in a molecule are fundamentally entangled. Classical models struggle to capture that exactly. Quantum models built from qubits can naturally mirror the entanglement structure of the real molecules. That's why one of the promising areas of quantum machine learning is learning properties of molecules and materials, things like energy levels, reaction rates, or material strength, and things like that. Many of the potential advantages we've discussed, like extra expressivity, natural handling of entanglement, the higher dimension feature spaces, are exactly what make quantum neural networks very interesting. They are the neural networks whose hidden layers live in huge quantum state space. Whether that translates into consistent real world advantage is still being explored, but conceptually, that's the promise of QNN. When we see potential advantages, kernel methods and feature mapping are one. Quantum feature mapping can define kernels that might be hard to compute classically. This cloud, in principle, gave improved performance on some classical problems, classification problems. Uh, for feature mapping can be used for complex data, like encoding data into high dimensional quantum state could reveal structure that is otherwise usually hidden. And then for optimization, quantum circuits are also being explored inside broader optimization pipelines. For example, in finance, logistics, or scheduling problems. In some cases, they may provide better approximate solutions or different trade offs. It's important to say that these advantages are still largely theoretical or early experimental stages. We don't yet have a long list of tasks where these quantum models are very clearly and consistently beat the classical methods. Uh, so current challenges is one is the noisy problem. We currently live in the era of noisy intermediate scale quantum devices. That means limited number of qubits, limited circuit depth, and significant noise. Many circuits that are appealing on paper simply cannot be run at full depth on today's hardware without the results being washed by the noise. Noise and error mitigation. Real hardware is noisy, like the gates are imperfect, the qubits are decoherent, and things like that. We can use techniques like error mitigation and in the future, full error correction, but these add complexity and resource overload. We also have barren plateau, which is a region of parameter space of a variation quantum circuit where the cost function's gradient becomes exponentially small with the system's size. making training by gradient boost methods effectively impossible. This is currently like out of scope of our session today. Sorry. Oh, sorry. Yeah. So, quantum machine learning is a very active research field with lots of exciting theoretical and experimental work going on. There are hopeful signs in areas like quantum chemistry, material science, and some specially designed learning problems. But for most everyday industry tasks like image classification, recommendation systems, standard tabular data, classical machine learning is still far ahead in terms of practicality. Like for yesterday's example, if you want to see, if you try to run that code, your QSVC is going to at least take few minutes to close to an hour, depending on how powerful your laptops are. But if you try to run with a normal classical support vector classifier, it's going to run in few seconds. At the same time, learning these concepts is now valuable because it helps you understand the frontier of quantum technologies. It puts you in a good position to contribute as hardware improves. Maybe by the time you learn much things about it, you will have a good hardware available because recently even China has announced that they're gonna have quantum computers put out commercial uses, and it also gives you a different way of thinking about the data, how to correlate them, and how to compute them. So for whatever we've learned until now, I hand over it to Navneet to show you on code how it actually works. Over to Navneet. Navneet, I think you're on mute.
All right. First of all, welcome to day three. And now we will go for hands-on session for machine learning. And I will try to give you the intuition behind everything, whatever Swati discussed today. It is quite a lot because it's so dense. But I will share the exact code which I will show you now, so that you guys can run on your own system, so then you can practice. But the thing is, uh, this is very dynamic basically. So I already mentioned this previously also, that whatever code I will share or we will share might not work for you guys. You have to do some debugging and try to find a workaround. Some of the issues I will discuss while I will share my code or first. Uh, as of now, let's start with something. In the lecture, we already talk about hybrid and classical loops, data encoding, and feature mapping. Swati has also discussed about something, variational circuits, QNNs, and some. She yesterday mentioned about quantum classifiers such as QSVC. So we will see some of them. So first of all, what we do, and let me share my screen first. So what's the agenda for today is I will share my I will start with something by creating a network anomaly data set, so that you can know how to do all the machine learning task and it. But as yesterday Swati already mentioned, this is a very basic artificially generated data sets for your own I can say your own uh, learning. This is good, but you have to change on real world data sets. You can use it. So I will go through each line by line for each code. For that, you can understand and you can use the same code while you're doing the talk sheets and other stuff. So first of all, we need a couple of things for running quantum machine learning code on Qiskit. First is similarly, previously we already mentioned about Qiskit. Then you need a specific Qiskit machine learning. It is very important because this is the library you need to have to run quantum machine learning Qiskit basically code. Then this is the Qiskit AER. This will allow you to run the simulators, either noisy or other thing. And one other thing is, if you have the Qiskit AER, you can also run on your GPU. And for your GPU purpose, you only, as of now, we have Linux operating system supported GPU execution. If you have any other operating system, it will not work. If you have Linux systems, then you can also use your NVIDIA graphic cards, and you can, if you have a multiple graphic cards, you can uh, I can say parallelize everything and ex- uh, s- distribute your task on multiple GPUs. So then this is for the runtime if you want to do runtime experimentation, and this is for something algorithm. These are for like optimizers we need for the optimizer which we need to do. And this is for your matplotlib for the plotting, and this is for uh, plotting, but it will show you as a latex format. And this is I just uh, show you like how to do in single statement whatever I have done above. I can do it in a single statement. So this is it. Let's start with the first one. I will run while I explain you code so that it will be easier to you guys to see how the entire thing will work. So now we import all the libraries we use in our QML pipeline. So and I will walk through the import slowly so you can see how each group fits into a full quantum pipeline. So basically, first we import NumPy, pandas. These are for the our classical math, or I can say Python libraries for linear algebra and random numbers. Then we have data for pandas. We use for the data frame. Basically, these two libraries are used for in this code is used for your uh, data generation, or basically the data set generation. This import is for you to time and to get the realistic timestamps, etc. And this is for your plotting. This is for the test to splitting your data into test and train and test splits. And these are the journal pre-processing, the standard and label encoders. So I will go through little by little later, but the main here is our quiz kit. So for the first one, this is like core quiz kit object, the quantum circuit. This is how we build our quantum algorithms, a sequence of gates applied to the quiz kits. Sorry, qubits use like quantum circuits. Then AER simulator. So this is a high performance simulator that pretends to be quantum computers but run on our classical hardware. We will use it to simulate the quantum circuit without needing a real device. And then we have noise. So basically, these are the tools. These are the noise tools for the noise model. So the noise model itself is a container for the different noise channels. We are defining the depolarizing error, and this is a random error that randomly scrambles the quantum states after a gate. So for the thermal relaxation error, I think we haven't mentioned previously this. So this is like this represents the decoherence over time. So where the qubit relaxes, or I can say back towards, if it is in a higher energy state, it comes towards it's a lower energy state, that is zero, and lose its phase coherence. Then next is uh, sampler. This is a primitive sampler, and it runs a circuit and returns your the measurements. This is one of the more critical import, I can say, or Qiskit primitive, which gives you the outcomes, basically your measurements and your probabilities. And our machine learning algorithm will use this object under the hood to evaluate the circuits many times. So it's like we have to run multiple times through number of shots to get our measurements and the probabilities. And the next is these are the very standard circuit templates. I can say the ZZ feature map, real amplitude, and poly feature maps. The ZZ feature map, just Swati explain you about the quantum encoding thing. It is it is used for quantum classical data into, like, transform the classical data into the quantum states using the ZZ entangling interactions. So this is used for directly converting your classical data into the quantum data, but using some kind of entanglements or the rotations. So this is how we generally use nowadays. And then we have the real amplitudes. It is a common variational ansatz. If I say ansatz, that means in loosely you can say it is circuit, but ansatz is a terminology which is very common in quantum computing, or I can say in quantum information field. So it is a layered circuit of rotation and entangle gates, basically. And we will use the real amplitudes in our when we discuss QNN. So yeah. Then the poly feature map is another type of ZZ kind of feature map, where instead of using ZZ entangling interactions, we use the poly operators like Z or ZZ to embed the data. And this is one of the most expressive among every encoding scheme, as they discussed previously. Yeah. So next is a import for QSVC. QSVC is our quantum spot vector classifier, and it is a similar, it behaves similar like your classical support vector machines, but its inbuilt kernel is computed through the quantum feature maps. And we have another is VQC, is a variational quantum classifier. In simple terms, this is our QNN, or I can say you can make a VQC you can train, or you can design a single qubit, sorry, a single VQC in a different type of way. For example, if you take and change some setting inside the VQC, and then you can make the QNN. Then if you want to change further, then it might become the deep QNN, or I can say in classical terms, deep neural network. Or if you further change something, then you can create a, maybe you create a quantum version of your generative neural networks or transformers, basically, where the attention mechanism can be used. It is a in I personally use VQC when I don't want to name any model. So if I don't want to say, okay, I am using quantum neural network, I will say VQC, because you can change the property of the variational circuits or a parameterized circuits and change its behavior. And VQC can be tuned in a different for different I can say uh, different functionality based on our own requirement. So it generally it combines the feature map, variational circuit, basically this variation circuit, or there are other Qiskit library functions which can behave like different variational circuit and our classical optimizers. Here we will use some optimizers. So other one is to calculate state fidelities. It is compute uncompute. Basically, it used by the quantum kernels. So we will use this to build kernels by measuring how similar two encoded data points as a quantum states. Then next is the fidelity kernels. This wraps the feature maps and a fidelity calculator into single kernel objects that VQC can use. So it's just a, like a kernel in our classical if in a classical SVM. So this is used for the optimizer. Uh, Cobala COBLA. Generally, I'm not able to pronounce it correctly always. So this is the optimization algorithm that does not require a gradient, and it is a very useful for training the variational quantum circuit, especially when the gradients are noisy or expensive to calculate, and we will use it to calculate our VQC model. We will see later. And the finally is the fake provider. This is for the fake backend that simulates a specific IBM device called Manila, and it uses real calibration data, including gate error, decoherence time, connectivity, so we can get a behavior similar to a real chip without actual deploying there and being a fully offline without going on the real quantum systems or pay something which are very expensive. So so this is like a single cell, everything you need to do the entire QML programming in this particular session. So here we have the classical data tools, we have quantum circuit building blocks, then quantum machine learning algorithm and different type of backends. For next, we'll see. For these are just a random, I can say, just to create a data set. So I just run it very fast so that you can see. You can just for your experimentation, you have to replace this code by a real a real data set so that you guys can have experience about how the real data sets, real uh, real classical data changes the behavior of different quantum machine learning algorithms. So I will focus more on the things which you guys need in longer term. Basically, other than this data set generation. So these all are basic things. So uh, let me complete this for this section will pre-process whatever we have generated above. It will pre-process and do some data cleaning, then data pre-processing, which will help us to generate a data better data frames so that our model does not have any effect or any limitations because of the data. So yeah, here we are encoding. This is not the our encoding which we previously discussed. These are like how to convert the different data set values or different types of data into numerical format. So this seventh cell is doing that only. Yes, you can I can say X contains or like yep. Yeah, here this is for the feature extraction. Basically, X contains all your input columns, and Y is the labels like normal port scan or DDoS thing. Then we will do something called train and test splits. Then we will do some feature scaling. This is very important because different types of different type of data have different ranges. For example, if we discuss, okay, age of a person, age can be from 0 to maybe 200 max if someone lives that way. But if we talk about the speed of light, then it is like from speed of light, or I can say rocket speed or something like this, which can grow very far and have very larger values. So we need to do sort of scaling. We are doing this in this one. Then we will this is very important step. We are using dimensionality reduction, because we right now, whatever quantum computers we have, we do not have large qubits in it. For example, if your data set have tabular, I'm talking about here tabular data set. So if your tabular data set have 1 million columns of data, we cannot put that 1 million columns into quantum computers, because first of all, we do not have a quantum computers which have that number of qubits. So what we generally do is we reduce the dimensionality of that data set to a limited number of qubits. For here, I used four, so that we only use in our data encoding, we are only using the 4 qubits. So there are because PC is very famous algorithm which transforms the large dimensionality data set into a smaller dimensional data. So nowadays people start using autoencoders for this, and they are much sometimes perform much better than this. But this is the least complex things you can do. So I have used this. So it's originally done. The original data have 10 features. So we reduce it into 4. So now current data have the transformed data have the shape of that data is 192 comma 4. That means 192 rows with 4 columns, and the test data is for 48 rows with 4 columns. So this is very important. This is like because we are in noisy or utility era of quantum computers. This step is considered as one of the most crucial. And generally, this will also define the quality of your data. If you, for example, you have a 1 million columns, you reduce into three dimension or 3 columns, then you lose your data. So you have to sum up, try to balance what kind of data you want to give to your quantum model so that it can perform better. So this is just to tell me. Okay, we already discussed about Swati discussed about what is why we need encoding, then what is what is amplitude encoding, what is angle encoding, what is basis encoding. I think there is one uh, fact about the amplitude encoding which Swati didn't mention. You can and the power of the amplitude encoding is you can encode the entire data of, or I can say the entire data of each atom present in this entire universe. Either it is visual universe, or which cannot be seen by us. You can whatever data their atom have, you can encode into 400 qubit using amplitude encoding. This is why people say when quantum computers arrives, we can have more powerful systems because of this amplitude encoding phenomenon. So just imagine there is no limit on data then. So right now, uh, current computers, classical computers have a certain limit to process the data, but quantum computers can practically can encode, or you can process the infinite size of data files. So let's start with some how we implement the amplitude encoding. So it's like we will take one example data point here. Let me run first, then I will explain. Yeah, example data point that and literally turn its component into the amplitude of quantum states. And let's walk through the thing. First, we already sample and sample from our reduced training data. That sample is vector from our PCA. After we print that original sample, if you see here, we already printed our original sample. We can see what is our current shape of that. Then we will I can say compute the Euclidean norm of and the length of that vector. Here is the Yeah, this is the original data. This is our normalized data, and this is the data which we padded. I will explain why we need the padded thing. So next we divide first yeah that yeah this is where we normalize our data. Then we are padding that data of padding the data into the power of 2. Because we are only using here 2 qubits, so we will encode our 4 dimension data into qubits. So that we creates a vector of zeros with the appropriate length for the state, and copy our normalized feature into the beginning of that vector. If if there were a more amplitude than the features, then the extra amplitude would be the 0. So we print the padded amplitude vector, which is the vector we want to load into our quantum states. Uh, then we build a quantum state with the number of qubits we calculated by default. All the qubits starts in the 0 state. Then we will call the initialize qc dot initialize. Uh, this instruction prepares the qubit into the states whose amplitudes are exactly the number in our padded vector. After this step, the quantum states amplitude directly encode our data points. Finally, we print the circuit. You can see this is how our circuit looks, and this is I printed so that we can see the values more clearly. So behind the scene, this will decompose a sequence of basic gates. But conceptually, this is amplitude encoding, and feature values turn into directly into quantum state amplitudes. So next is the angle encoding. Uh, we will look at the angle encoding, which is often more practical. And first of all, I forget to mention about this amplitude encoding. This is although it can accommodate a large number of data, but it is really complex. Even if you are using amplitude encoding in the classical computers, this might take your execution might be days or weeks because of the complex data preparation process. And now with angle encoding, which is more often more practical on the real hardware as well as on our on our classical systems as well. Here, each feature becomes a rotation of on an qubit. We again take a single sample from the reduced training data and print it so that we can see the values. Then we find then we find the minimum and the maximum feature values in that sample. We use these to rescale the features into the range to 0 and 1. We subtract the minimum uh, and divide it by the range. We identify this tiny constraint in the denominator just to avoid the division by zero if all values were same. So once we have all the values between 0 and 1s, we multiply them by pi to turn them into the angles. So basically what we are doing is we are turning them uh, into the angles. So each feature becomes the number between 0 and pi. Then we print these angles so that you can see what what will become our rotation parameters. We set uh, we set the number of uh, number of qubit for equals to the number of features. So we have one qubit per feature. So this is like we are although rotating into the angles, but we need, if we have four features, we need four qubits for its execution. So then we create a circuit with the multiple qubits. Then we loop through these angles, and for each index angles, we apply an uh, rotation with the theta angle to corresponding qubits. So the first feature rotates the first qubit. The second feature rotates the second qubit, and so on. So this is, in the end, you will have the rotation, and you will get you can get the circuit, and you will see the rows of RY gates on one qubit per feature. So and these are the angles proportional to their feature values. So that's the angle encoding. And this is a very classical feature to encode into a rotational angles on a qubit. Then we have a very simple one, the basis encoding. So which is conceptually the most simplest one. We start with we will start with the list of bits, and I can say, for example, 0, 1, and 1, 1. So we will take these numbers. You can think of these bits as a representing yes or no features, like, or it is a night, or it is a day, or it is raining, something like this. And we can take the length of this bits in bit list to decide how many qubits we need. So for each bits its own qubit needs its own qubit. So 4 bits we use for qubit. We loop here also. We loop each. We create a quantum circuit, and with the many qubit. Initially all the qubits are in the state of 0, as I previously told you. So we loop over each qubit, and for each position where the bit is 1, we apply the X gate to that qubit. An X gate flips the state into 0 state into 1, and if the bit is 0, then we do not do nothing, and the bit stays at the 0 state. At the end, if we have if our byte string is 0, sorry, 1 0 or 1 1, our quantum state is, it looks like something like this. Then which and you can see in the printed form, we have qubits have all the X gates. And because we do not have any X gate on qubit 1, so it looks like it does not shows any gate. So this is basic basis encoding. 0 is mapped to a basis state of 0 state. 1 is mapped to the basis state 1. And basically it is a one to one mapping, in other words I can say. Then we have very important feature maps. These are primarily these are the circuits which are designed to encode the features. So here I will show you how to construct the ZZ feature map, and it is a very popular feature map in QML, and it and it's mostly used nowadays if you are using Quizkit machine learning tool. First, we set the feature dimension to 0. Oh, sorry, to feature dimensions to 4. Then, because we reduced our data into 4 components, that's tell that feature map tells the feature map to expect 4 classical inputs. Then we create a feature map with 2 repetitions. That means it will 2 repetitions and linear entanglement. So 2 repetitions says we repeat the feature map block twice, adding the depth. I will show you. Let's me. This is how complex it is. So adding the depth and expressivity to the encoding, and we have we are using the entanglement as a linear entanglement. So, which means the qubit is entangled with its with its neighbor in a chain format. So, zeroth qubit is attached with one first qubit. The first qubit is attached with the second, and so on. It is like this. So this feature map does two things. It applies a single qubit rotation, then that depends on the input feature. It applies a data dependent ZZ interaction between neighboring qubits, creating the entanglement that reflects the correlation between the features. Finally, we decompose the feature map into the basic gates and draw it. So you can see this is our ZZ feature map, and this is converting our classical data into the quantum state with entanglement. And generally, and in this later in the code, we will use this particular part. And another feature mapping is the poly feature map. Previously, we see the ZZ interaction. Here, we will use the poly operators to map the data. So again, we have the 4 dimension because we our data is contain 4 component. So here we are defining our polys as Z as ZZ. So this particular feature, same thing in here also. The repetition is our entire quantum circuit or entire feature repeat repeat the pattern twice to increase the expressivity. This is the very critical hyperparameters also in every feature maps. If you increase the number of repetition, you can get much more better expressivity of your data, but your performance or your cost will increase with the increase of a repetition, or I can say depth. So when I say repetition, that means it is repeating again and again same thing in multiple way. So it is like this. So and the poly ZZ is this feature might include the single Z terms, single qubit Z term and two qubit ZZ terms, both depending on the input data. Conceptually, it is a similar to the ZZ feature map, but expressed in more journal poly frameworks. By choosing different polystrings, you can tailor the feature map to the structure of your problem. Particularly if you are doing genomic sequencing, you need a different I can say different poly structure. And if you are doing something called maybe autonomous vehicle trajectory prediction, maybe you need a different then. Then in the last again, we will decompose. We are decomposing our circuit to see. If you see, this is more. It have a more gates than the ZZ feature map. Now we will go to actual circuits, or I can say model, toward the model building. So we will use uh, the parameterized gate, and then we will use the trainable parameters, and which are optimized classically. So the journal sequence is input the data, then input the classical data, then encode the into the feature map, then we process through the variational circuit with parameters theta, or you can have multiple parameters in it. Then extract the values, or measure the values, and then extract that values as a classical output. And you can update or minimize your cost function. So let's start with real amplitude ansatz. So this is how it looks. So basically, what this code is doing, this is also something behaves similarly like this repetition, and it needs exactly same number of qubit your feature map, because this is the this has the this has the this has a output. Whatever output of your feature maps is considered as the input for your variational circuits. So here we what we are doing is we are telling the function that we are using 4 qubits, and we want to stack uh, your variational circuit two variational circuit layer with the rotation as well as the entangling gates basically. And if we generally do not give this entanglement as explicitly, then by default it generally do not use any entanglement, and entanglement generally remains none. Or in some cases, it will be a full entangle. That means each qubit is linked with every other qubit. So it is like this. Uh, Yep. I will explain like what's going on here also. After this, we are printing the number of trainable parameters. Each parameters corresponds to a rotation angle. So it plays the role as or roles of a weight in a neural network. The more parameters we have, the more flexible the model is, but also the harder it is to train. We also print the circuit depth, which is the number of layers gate applied to a sequence. Depth is more important because the deeper the circuit, uh, the more the expressive your model is, but the more vulnerable to the noises in real world. Basically, the more if you increase if you use this another layer here, it can increase the power of your model, but because these gates are noisy gates, so in real quantum computers, the performance will decrease. And you can see there's a layer of parameterized ry rotation on each qubit, and followed by the entangling c nodes. This is our QNN layer, I can say, where the qubits are neurons, and rotation parameters as a weight. The layers of a gate as a neural network layer. So these are the layers of your neural networks, and the values here are the rotation as a weight, and the qubits is your neuron. So in if you try to map this as your with the classical neural network, then there is something, the parameter shift rule. We demonstrate the parameter shift rule using simple dimensional function. This mirrors the formula we saw in the lecture, but in a concrete example, we define a theta function basically that returns a cos theta, which is the exact analytical derivative of sine theta. Then we define the parameter shift grade theta. This function implements the parameter shift formula which we see in that slide. So here we will let me run first. Yeah. So inside this we compute the function theta plus here we are computing the f theta plus pi by 2, then we are subtracting from it from theta minus pi by 2 and whole equation by divided by 2, and then we create a small list of theta values from 0 to 2 in this code, and then we print that header line. Yeah, if you see this, yeah, uh, the loop over each theta, we compute the f well. Where is that? Ish. Yep. For each theta, we print we print these values so we can compare we can compare them. You can see here when we run this, we will see that the two gradient and the parameter shift gradient agree very closely. This is exactly the trick we use for the quantum circuits to get the gradient of expectation value with respect to parameters. We evaluate this circuit twice, and once the parameter with the parameter shifted by pi by 2, and once with the shifted by down parameter, basically rotate opposite side uh, by pi by 2, then we are showing these results. So this is generally the ideal cases, but in noisy conditions you see a lot of errors and everything. So this is how the parameter shift thing looks. And so this is visually confirmed that the parameter shift rule gives us the correct gradient, and it's the method we can use for the variational quantum circuits when we need the gradient for the training. Then you can see it is overlapping with the calculated one. The next is the short values. I already mentioned about the short values, like how many times we need to run the code. But for the example, or I can say from here, uh, I will give the short value to 10, then 100 or 1000. Although it is how I can interpret these values is here the samples are we are sampling very few, and that's very fast, but very noisy also. And when the short values are 100, it is more stable, more stably estimates the probabilities, but it takes longer time. And if we give much larger short values, it is more precise to estimate, but the higher the computational cost. So this is it depends on you how many shots or your accuracy, or I can say you are happy with while you are testing your algorithms. So so it's basically depends on your execution or your problem which are you solving. So this is just from here we will I'm creating a list so that we can have a result of above VQC which we have discussed. So I will start with the ideal simulator. Basically, we do not have any other properties. Basically, no gate errors, no decoherence. It will give us the perfect measurements, and this represents the theoretical quantum advantage, or I can say theoretical quantum computer also. So this is in other words, I can say this is the best case scenario, and in theory, it is perfectly functioning like a fault-tolerant quantum computers, which are in real world at least 10 years down in the future, and in later in the I can say later in the execution, I will show how we can how we can add the noise in this ideal simulator to get what we want, or I can say get what current quantum computers are capable of doing. Uh, Let me change this to second. Yeah, here I'm training the VQC model. Basically, whatever we discuss above, we are doing here. We are using the quantum ZZ feature map to encode the classical data into 4 qubits with two repetition. Basically, the depth of the circuit should be fixed as 2. Then we are using the entanglement as a linear. So 1 qubit is connected with in series basically, and here we are using sampler. This sampler is taking the R number of shots which we defined earlier, which is 10, 100, and 1000, and this is our simulator which we define here through a AER simulators. AER, I already told about you what is AR simulator while I was discussing the imports. Similarly, then we are calculating the fidelity using the compute and uncompute. Then we calculate the quantum kernel using fidelity quantum kernel. Then we like the classical machine learning. We are giving our model, which is QSVC, basically the quantum state vector machine or classifier, and fitting that function using our reduced data. Basically, our reduced data is containing 4 rows and 194, I think 195, sorry, 4 columns and 195 uh, rows. 4 columns, 195 rows. Yeah. And then after training, let me run this also. It will take at least 1 minute to run this, so we can see. And this is not, you cannot judge the accuracy based on our synthetically created data set. Might be it is very high, or might be it is not very high. Let's see. But you can get uh, similar, or I can say you can use a similar kind of performance matrices. For example, your accuracy, your F score, your recall values, your precision, everything to calculate to use while using the QSVC. So this result shows that while training QSVC with 10 shots on ideal simulators, we are getting this much of accuracy on our synthetic data, and might be it will be a very low in this, or might be the same. So as a this shows that if we increase the number of shots on ideal simulators, our QSVC does not change the performance. Only the cost is increased, nothing else. So this also concludes that uh, we cannot we cannot have a performance gain while increasing the number of shots. So, yep, now you can see all three are computed, but even for 100 shorts, there is no change in QSVC performance. And similarly with 1000 also, and even for 10. So we can conclude the QSVC with particular for this given data set does not gives any performance benefit while doing this, while increasing the number of shots. So even we can get our best accuracy using the 10 shots, so it is much faster. Then there is VQC. In other words, this is the QNN of quantum neural network. So this is also have a similar setup. Here we are using the 30 iterations. In other words, 30 epochs in classical machine learning terms. The similarly, we are encoding the yeah, it is very fast. Sorry. Yeah, we are encoding our classical data into using the ZZ feature map. You can change it to, for example, if I want to change it to poly feature map, I will let's first see what is its accuracy. Okay, with VQC, which is very tiny, shows very poor result. You can see that with when we have a 10 shots, it gives us 6% accuracy, but when we increase the number of shots, the accuracy is zero. So either the system have some problem above, or the model does not predict anything. So you can test it with the change with change the number of uh, uh, iterations to maybe 100. We can increase the number of repetition to 6, and similarly with here also we can increase the number of layers to 6 also, and it will take a lot of time. Now if we see, let's see what is. So basically, when we increase the number of repetition, it is increasing. In other words, it is increasing the number of layers in your neural networks. But and if we increase the number of qubits, that will increase the number of neurons or bases or biases. It is like this. So, so similarly, we are testing its performance here. Now you clearly see it is taking too much time now, because we increase the depth as well as uh, increases circuit depth here, as well as then increase the layer number of layer here. So this is how, yeah, it's again decreasing. Let's see it increases or not. And another thing. By the time I will explain by it is running, I will explain what is happening in here. In this is just comparing like the both result of QSVC as well as VQC on our given data set. Nothing else, and it will plot, and it will even give you the image. And this is the noisy when we create our simulator noisy. So what we are doing here, we are initializing our noise model. This is the noise model given by the QuizKit itself, but we are defining the different noise channels. So different noise channels which gives us the different properties, or which makes our simulator to behave differently. So if I say let me first see, is it working? Yeah, almost. Yeah, now you can see it is increasing little bit, but might be for 1000 iteration, it will decrease. let's see how it works. Summarizes this one. Yep. Now, let me, yeah, this is the ideal one. Basically, I am defining the depolarizing noise. This means we are giving uh, these value, that is this value saying that the qubit 1 has 0.1% of error rate, and this shows that uh, our uh, our qubit 2 has the 1% of error rate. So and this reflects the reality that qubit gates are typically more noisier than your single qubit. And we set this T1 as a thermal times, or I can say T1 and T2 times in microseconds. Sorry, micro, or I can say a nanosecond, depending on how you say. So here we are giving 50 microseconds, and here we are giving, if you increase it, it will increase further the noise error rate, further increase the noise error rate, and making more difficult to get better results. So these approximate how long a single qubit gate or a two qubit gate takes, and the longer the gate time means the more time for the decurrent to act. So basically, the more the time you give, the more the interaction or error will be there in the thing. Using these value, we are creating these both errors in the system. And then in the end, here we are combining both the errors into both the error channels into one qubit and two qubit gate. That means very time we apply a gate, we apply both type of noises. So you can increase in the same model, you can increase other noises. There are some noise called bit flip, phase flip, amplitude damping, coherent, decoherence, lot of different type of noises you can test with. Before that, let's see how uh, our accuracy. Yeah, before it, our model little bit again decreases its performance, but this is like a representative model. Maybe some other data set, it behaves much better. Even the same model, same depth, everything. So you guys can test by yourself, and this is like comparing its performance in ideal simulator, like with QSVC and VQC. So yeah, here I'm like, we are creating that thing, and these are the basic gate, the most smallest unit I can say of gates. And we are creating, in other words, we use a generic terms, generic gate terms, and we are rotating these as X, RX, or RZ rotations. We are giving them, and then we are calling this model into our simulator, so that when we run the simulator now, it has this property. It behaves like it has noises. So when we run the circuit on this backend, they will behave like the running on a noisy quantum computer, or an noisy time quantum computer, rather than a perfect, like this results is on perfect one, this results will give us on noisy one. So same thing, if we see, it took at least how many times, 2 minutes to run for VQC, and at least one and a half minute to run on sorry, yeah, QSVC. In when we are using a noisy simulator, let's see how much time it take to run. Okay, this is, oh my God, this is noisy background. Okay, I need to run this first. Mhm. Then, yeah, it started now. It will take more than 2 minutes for sure. Even though we have, yeah, we have less number of layers and everything. So this is exactly everything is same. Only we are using the noisy simulator here, and we keep our everything same. Whatever we have done previously, we will done same, but it will behave differently. Let's see on the 10 shots. Uh, for VQC, the amount of noise we have specified does not have any major effect. Let's see on how the number of shots will behave. Um, this will definitely take longer time than after. Yep. Yeah, even for Honda, there is nothing, no change in with VQC. Even though we are using some noises, but if you increase the percentage of noise, it will behave differently. Definitely, that is, you can play with these numbers, T1 number, T2, then the depolarizing error, the basically the error rate. The more you can increase, you can see the more degradation in the code. Oh, sorry, in the performance. Basically, in this particular example, it does not show anything for us. You can say you can see here the accuracy further decreases, and for other two, it does not work at all. So, yep, you can see that earlier. This is our, although the graphs does not look good, but you can see there are clear difference in ideal as well as the noisy. But in VQC, there is no change. Maybe you can change in another setting. And the final one, which I want you guys to know about, it is a fake backend thing. And for this one, I'm using the Manila, fake Manila, and for this, it mimics the real quantum computers or IBM computer basically. So it creates the fake. This creates this statement creates the fake Manila and simulator, and this simulator has the same number of qubits as a real Manila device. And and fun fact is for this, you can see the IBM gives their quantum computers name based on the different cities of the world. So you can see IBM Brisbane also. I think Brisbane is retired right now. So maybe previously we have IBM Melbourne, then we have IBM Mumbai, then we have IBM Tokyo, and this is the Manila, IBM Manila. So based on different properties, if they have different properties, they give the name to that computer based on the different cities. And for this Manila one, it is like this particular simulator have, as I told you, same number of qubits, same type of connectivity. Same, if you remember, first day when I show you that blue connected graphs, sorry, map kind of thing, that is the like connectivity maps and the calibration data also, which means different type of gate errors, how much the coherence times is there, and it's everything. It behaves like that way, and this will gives us, for example, if you see its thing, the basic gates, it supported is this only. Then the coupling is 0 1 zeroth qubit is connected with 1. Then similarly vice versa also, then 1 and 2. But if you see 0 is not connected with 2 or 0 is not connected with 3, so either it is using I can say chain coupling map or something different coupling map. So it is like this. So despite of having how to change that this function, just you have to import that and change sorry, you have to initiate and just you have to change the backend or I can say the simulator the type. The rest will be the same. So if you want to do a noisy one, then you have to just change you have to just include the noise model into AER simulator. If you want to use the fake, then you have to change the backend here only, and rest the code is the same. So if we run this code, it might run faster, but still it doesn't it still have a very lower performance in my terms, or maybe it will work better than other implementation which I have shown you. So let's wait for this. And I think I have showed you. Okay. Optimizer, I already showed you. We are using Copala. Yeah. Here we have like 30 trace epochs. Max iter you can make it 100. That means then your optimizer will work for 100 iterations, or I can say 100 epochs. So it depends on that way. Yep. Here yep. Even on the Manila fake backend, our code works almost similarly. So VQC concede comes up better in terms of on our synthetic data set. I don't know about other data sets, but here it is performing better than our journal basic or a tiny QNN. So if you see, this is, I think, exactly same performance which we have already shown. Why I have shown you the three different implementations? It will help you out to first ideal is to help you out to check whether your code or your model is working or not, basically working fine or not. Then you will test your model on noisy data or on noisy computers. Once that is also running, then you can use your fake backend or fake backend, so that you can choose a specific quantum computers to run your code or run your model, because we have to do this because not every quantum computer is built for your thing, your model. So for example, I'm just giving you example. IBM Tokyo, if is capable of running VQS sorry VQC, and might not be able to run the QSVC. Similarly, if IBM Brisbane is able to run a small, I can say the quantum transformer model, but it might not run your KNN, quantum KNN model. So we have to choose, or we have to pick. Or sometimes there are some computers which sometimes have a large number of errors. You do not want that. For example, in medical applications where a single 0.1% of accuracy or precision can make a difference in someone's real world someone's life. We need a less computer which is less prone to the quantum noises. So we have to choose based on different properties of quantum computers, which which algorithm is suited for which quantum computers. Because right now we do not have a general purpose computing. Like we have our laptops, which we can do whatever we want to do. But in real IBM computers, we do not have that luxury. So if you see uh, here also in fake backend with 10 iteration with 10 shots, model does not work at all. But with 100, it's little bit it started, and with 1,000 shots, same code, same everything, same properties, it starts growing, or I can say starts improving. So it depends on how many number of shots you want to give. It depends on that, and you can see the change in accuracy and all in this. So I think this everything what I have shown you is all we discussed with Swati already discussed the theory behind or a concept behind that kind of thing. I covered, I think, hybrid, how we can use the hybrid optimization. Then I think I already covered encoding and different encoding schemes, feature maps also, two different quantum algorithms. There are number of quantum algorithms. You can have a autoencoder, quantum autoencoders. You have a Pegasus, QSVC. You have quantum kernel, sorry, nearest neighbor also. But we are using IBM Qiskit. It supports only very few quantum algorithms basically. So as of the session, this is the end, but I will show you one other thing which is, I think, which might be helpful for you guys.
In the meantime, that I pull my screen up, Navneet, there's a quick question from Benjamin.
Yep.
Um, One sec. Which is better to use for a noise model, a user-defined noise model that you talk about, or the fake backend? Because you say fake backend is basically representing the IBM hardware, so it should already have noise.
Yep. For this question, I can say because as I told you, not every computer have a same type of noise. For example, one computers does not have it is a hypothetical thing, but does not have a decoherence noise, or does not have a bit flip error, or does not have a depolarizing noise, and one have all of these. So that's why I cannot say that, okay, or you cannot say that, okay, Navneet, fake Manila, in Manila it is working, but in other computer it will not work. So that's why we generally use not generally use the fake backends, but fake backend is to when we actually want to deploy. Before that, we want to see, okay, how our model will behave based on our on that particular computer. That's where we use the fake backends. But for other than that, for our testing, our benchmarking, our evaluation, we use our own defined noise models, which have where you can put number of, or we can you can increase the number of I can say percentage of noise. You can decrease the percentage of noise. You can add more number of type of errors basically. For example, in same computers, you might have sorry, same experimentation. You can check with depolarizing noise. You same then you can add amplitude dephasing, or phase damping, or bit flip, or phase flip, or thermal relaxation, whatever. But might be in fake backend, and out of six or seven, only three is affecting more. So it is like this. So it depends on you. If you want to deploy on real quantum computer right now, you can, okay, mimic that thing and check, okay, what you can expect. instead of spending, because IBM quantum computers are really, really expensive thing to run. So I think if you want to pay, you have to pay 1 minute for one, at least for 1 minute. It's I think $98 last time when I check. I don't know whether they reduced now or not. So this is the question. Any other question?
Hello, sir.
Yeah,
Hello,
yeah.
sir.
One by one, please. Let me. Yeah,
Yes, sir. Can I say now?
yeah, yeah, yeah. Yeah.
Actually, my question from that encoding portion, like
Okay,
when we need to like for some particular problem, we can say that
okay.
maybe there are amplitude encoding or angle encoding or basis
Yeah,
encoding. We need to use that. Is there
yeah.
any like types of problem we can say that this is particularly for that encoding?
Okay. It depends on
And
your, I can say, basically you want to ask like when to use which encoding scheme. Is it
yes,
that?
yes, yes, sir, yes, sir, you are right.
Yeah,
Yes,
yeah.
sir.
So I can say if you want to use, if you want to have a like very powerful, basically I'm talking about the classical computers right now. For example, you have a very big cluster of the classical computers where you are running your experimentation. Then you can also use the amplitude encoding because you have a very large data set. You want to use only some number of qubit, but your computers can calculate the more quantum circuits. But for example, in real world or for example, you do not have a large number of data set, large number of data. So just you want to have, okay, I can instead of compactness or efficiency, I want to detect more pattern in the data. So then you will, okay, I want to use angle encoding. So because angle encoding or feature maps, basically these angle encoding or in other words, feature maps is the advanced variant of angle encoding. It is a loosely terms. It is not exactly, but if you say in your head how to understand it, is like feature maps are the advanced variants of angle encoding. So, but angle encoding can express some data or can find some patterns, but feature map have the ability to use rotation as well as the entanglement combined to get more data, more patterns. For example, uh, because the quantum model is directly proportional, or I can say directly dependent on the feature maps or how your quantum is encoded, data is encoded. The more expressive your feature maps or your encoding is, the more better your uh, model will behave. So it is how you what is your requirement basically. If you I will choose if I need it my if you can see, okay, my data have very complex patterns inside it. You might think, for example, uh, this is which we say a DNA. So DNA have very complex things. So although it have very large, for example, for my DNA, it might have 1 million strain. The length, the character length is 1 million. I can put it that 1 million into 32 qubits, but it does not give me that my model does not have the power to get the patterns out of it. For example, some particular gene in my DNA have enable some better things in my body, but maybe some different small genes have uh, cancer causing basically some cancer causing gene. So how to detect those delegate patterns? For those kind of problems, we choose more advanced feature maps. So because feature map have the ability to express or I can get that particular pattern. So I choose feature maps over amplitude or even for angle encoding. So it basically depends on your own problem. So if you do not want, okay, you just want to calculate the things, or just want to compress everything into you do not care about the precision, you only care about the accuracy, then might maybe angle encoding and amplitude encoding is better. But if you care about the precision as well as accuracy, you go for the amplitude, ZZ feature map or poly feature maps. It depends on the. I think it will clear.
Yes, sir. Yes, sir.
Yeah,
The summarized
yeah,
thing, like I
yeah.
understood, like for more or complex pattern is there is in data set, then we can
Yeah.
use a feature map like the ZZ
Yes,
feature map is there.
yes, yes, yes. But
Sometimes,
ZZ feature map also come up with their own problems. Then you have, for example, then you have to limit with the number of qubit you have in your system. So you have to do that kind of thing.
okay, sir. Okay, sir.
Yeah.
Hi, sir.
Okay. Yeah, 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 yeah,
Yeah, I have one question.
yeah.
That you just said we can use a feature map in order to get a high accuracy result. Yes. When
Not
you
high. Yeah, you care about accuracy. It's not high accuracy, but it is if you care about accuracy more. It is like
and
this.
and actually the feature map used to transfer
Yeah.
the data into the high dimensional feature space.
Yes.
And while
Yes.
transferring the data into the high dimensional feature space, doesn't it increase the computational power?
Yeah, that's where I'm talking about. Like that's where it comes. It's have their own limitation. The entanglement. When we do something with entanglement, or we want to increase, expressivity, the entanglement, or I can say the computational power, or the cost will increase. But when we are talking about here, because we normally run our quantum algorithm on our local computers, basic computers, classical computers. But when this will be very fast when we are at the quantum computer scale. If you, I think you understand or not. Did you understand?
Yes.
Yeah, yeah. When you are using the quantum computers, that depth, one or two depth does not make sense for them. It is for nothing for that. But for our classical computers, if you increase the repetition for 6, it will be like maybe it take a long ages to run. Maybe if you make it really 20, that might be your computer will be shut, like overheat and shut down. But for 20 repetitions, it might be very, very simple for quantum computer. So although it will increase the cost, but we generally in a business use case, we compare like cost versus the time, or these kind of things. We always have a balance or trade-off between either performance or cost, or it is like this.
Thank you, sir.
Yeah,
And there is one question also, like
yeah,
in QML, does there is backward propagation mechanism?
yeah. You can create, but it is not a genuine backward propagation thing. It is not a like actual thing. You have to do it classically.
Yeah, and while running the model or the QML model as a classical
Yeah,
way,
yeah,
there might be like information into the not only in T and
yes.
in the T state, and how we can compute or like capture the information of the T minus 2 state.
This is not, I think I don't know about this. I need to learn because generally I'm not dealing with the noise right now. So I think I will get back to you if you send this same question in the discussion form. I will get back to you. I will give you the answer after some
Oh,
time.
okay, sir.
Yeah,
Thank you,
yeah,
sir.
yeah, yeah. Uh,
Yeah, Russell, do you have something to say? Are you speaking? We can't hear you. Your volume is very low.
Okay,
இல்ல
by that time,
You can type your
அதான்
question
அதுதான்
in the
அதையும்
discussion.
பண்ணிட்டு தான் இருக்கேன். ஆமா ஆமா ஆமா.
okay, by that time, I will show, I will give you once, almost we are end of our session. I will show you this resource, which is best resource you can find right now. As of now, it is like Quizzkit community, GitHub. This is the Quizzkit machine learning. Uh, it have everything from start to end. Whatever we teaches you today, even though even Swati and me combined together, we cannot cover everything, and we still learning also. So always keep an eye on this version, whatever your version are using, as well as these tutorials. This is the quantum neural network version. They are like how you want to use in class in a different format, basically in you different problems, classifiers or regressor, then how to train your quantum models on real quantum, then this is the QSVC kind of thing. This is the GAN model. This is the how you can connect. This is the this particular this and this one will teach you how to create a hybrid models, purely hybrid models. This is the advanced Pegasus version of QSVC. This is your how to train your kernel training mechanism. This is how to save or load your thing. This is how to know whether your model is showing basically overfitting or underfitting. This is CNN, basically QCNN. This is autoencoder. This is Bison. These are all you can learn. You can click and learn. These are the like more advanced. Whatever we touched on this lecture is a very basic. So either you can you have to once go through whatever we teaches, then jump it here or whatever you prefer. But this is a very important resource for this. So I think if no one has other questions, so we can end the today's session. And if anyone have any question, please put on in the discussion forum. I will try to answer as much as possible, fast as possible. Uh, I just saw one question.
Yeah, Russell is asking, I am at the beginning of my work on quantum machine learning and I am using Windows OS. Is it critical to use Linux?
I
Just to
will.
be quick, he's using Windows, I'm using Mac, and we also have Linux.
So we have all three systems basically with us. But if you are using Windows, you can use something called WSL, which is Windows Subsystem Linux, which will allow you to use every functionality which Linux provide on your Windows system itself. If you just search basically WSL2, just install this one. And it will create a basically a virtual machine kind of thing, and it will help you to do Linux or do whatever you want to do through Linux. But only use Linux if you want to do if you want to use GPU. Otherwise, it does not make any sense for me right now. If you have a GPUs with you, go for it. Yeah. Any question? So I think this is and for the today's session. Yeah. Swati, you can stop recording and we already shared the task sheet with you. Try to do whatever optional task we have mentioned there. Maybe it will helpful for you guys. Okay. Thank you for today. See you tomorrow.